Instruction addressing. To complete the entry of a relay type instruction, you must assign an address to each instruction. Address indicates what input is connected to what input device. Okay, so this is the input device, the limit switch, and is connected to 312. Let's say this one is the third slot and 12th point. And the address in the memory is I312. Okay, so this is the image table that shows where is the address. So the contact evaluates this memory bit in every cycle and see if we have any updates. So at this moment, it checks the memory bit is 1 is true. So the logic here holds, and the output will be updated and will be true now. So the output image table will be updated to 1, and the output module then will energize the associated field device with that bit memory. Address indicates what output is connected to what output device. The assignment of an I/O address can be included in the I/O connection diagram. So this is the I/O connection diagram, a physical connection of devices. And basically we are using squares and diamonds to show what is the bit address in the memory of these devices. Inputs and outputs are typically represented by squares and diamonds respectively. So here it shows that this push button 1 has address of I45 in the memory, and this let's say pilot light has an address of 036. Branch instructions. Branch instructions are used to create parallel passes of input condition instructions. A rung will be true if either instruction A or B is true. So either of A or B, it is like or condition here. Then the C will be true. Parallel branches can be used to allow more than one combination of input conditions. So here, either A and not to B, so this is a negated contact. So either A or not B should be true, or C should be true. We are moving from left to right, yes, from either of these passes. And then when the logical continuity holds, then the D will be energized. Output branches allows a true logical path to control multiple outputs. So here we have multiple outputs C, D, and E. Either A or B provides a true logical path to all three output instructions C, D, and E. So if either of A or B is true, then all of these will be true. Additional input instructions can be programmed in the output branches. So here, to have E energized, we must have correct, we should have a true logic on D. Input and output branches can be nested to avoid redundant instructions and to speed up process scan time. So here we have nested branch. So this is the main drawing, okay? So we have three main branch, have these three main branches here, and we have nested branches, yes? So these are the nested one and 2. We have two nested branch. Nested branch starts or ends within another branch. So this one starts and ends within the first main branch, and this one starts and ends within the second main branch. In some PLC models, the programming of a nested branch cannot be done directly. However, it's possible to program a logical equivalent branching condition. So here we have a nested branch here in this program, the ladder logic program. But in some PLCs, it's not possible to program like this. So we have to find the equivalent one. And this one is the equivalent version. So see what is the path, yes, if we go from left to right on this nested branch. So we have to go through A and then D and then C to reach Y. Okay, so A, D, C, and then Y. So if you want to avoid the nested branch, so we should have the same paths. So we should have A, D, C, and Y. Yes, so A, E, C, and Y. So we avoided that nested branch, but still we have the same logic on this equivalent version of the basically this program. There may be limitations to the number of series contact instructions that can be included in one rung of a ladder diagram, as well as limitations to the number of parallel branches. Okay, so again, it backs to the PLC specifications, and some PLCs have some limitations in the number of contacts in series and branches in parallel. For example, here, the maximum number of contacts we could have in series is 10, and the maximum parallel lines is 7. Okay, we cannot go beyond these limits, and we need to find the equivalent. The PLC will not allow for programming of vertical contacts. Okay, so here we cannot program a ladder logic diagram like this, yeah? So we cannot have a C in the vertical path. This is not allowed, okay? But we need to find the equivalent one, yes? We need to find the equivalent, and let's see what is the Boolean equation, yes? Boolean equation is that Y is equal either A and D should be true, so AD should be true, or, so plus means or here, so or B, C, and D should be true, so this is B, C, D, or B and E should be true, or A, C, E should be true, yes, and again we are moving always from left to right. So to have the same logic, we could have this program. So we have 4 conditions, then we could have 4 branches in parallel, and on each of them we could put contacts in series. The first one A and D, the second one B, C, D, third one B and E, and the last one A, C, and E. So this one is programmed to eliminate vertical contact, yes? We cannot have vertical contacts in ladder logic programming. The processor examines the ladder logic rung for logic continuity from left to right. If program as shown, contact combination FDBC would be ignored. Yes, so for example, if we had in mind to have a condition of FDBC, then the processor of the PLC completely ignores that condition, and we need to reprogram it in a correct format. So this is the Boolean equation, and you see that we have also that FDBC in the mind of the programmer. Yes, so it was in the mind of the programmer, but programmer just programmed it wrongly. So the equivalent could be this one. Yes, so we have that FDBC pass, and we included all of these conditions. Yeah, so we cannot go from right to left. Okay, we cannot move from right to left. We should always go from left to right. This is the way the processor of the PLC examines the program. Internal relay instructions. An internal output doesn't directly control an output field device. Okay, so this is the internal relay. It's just auxiliary coil, and it has an address in the memory. Yes, but it's not associated with any field devices. The advantage of using internal outputs is that there are many situations in which an output instruction is required in a program, but no physical connection to a field device is needed. So it helps us in programming, specifically for ladder logic programming. It helps us to enhance, to improve, and to bring our programming to the next level. But basically, without using this type of internal outputs, we won't be able to enhance our program and make it advance. It's basically just borrowing a bit memory from the memory. Yeah, so we need that memory to increase the performance of our program. So for example, SLC 500 controllers use bit file B3 for internal bit addressing. Okay, so this is the file B3. But for different PLCs, we have different basically addressing. Yes, so you will see later when it comes to the codices and the TIA portal how we could use this type of internal bit addressing. Internal relay used for a program that requires more series contacts than the rung allows. So this is one application out of many for the internal relay. As we said, some PLCs have limitation in number of contacts in series and parallel branches. So let's say we have a limitation of 7, so we cannot have more than 7 contacts, but we need to have 12 contacts in series. So how could we program it? Then we could use the internal relay coil. Okay, so in the first rung, we have 7. In the second one, we are using a contact associated with that internal relay coil. Yes, so it has the same address. It has the same address of B313 as the coil. So when these 7 contacts are true, then the internal relay coil will be true. This contact will be true, and we'll go to check other contacts from 8 to 12. And then finally, if these are true, then the discrete output, which is a real field device, will be true and energized. This PLC allows for only 7 series contacts when 12 are actually required for the programmed logic. Programming examine if closed and examine if open instructions. Examine if closed or XIC instruction. Both the normally open and the normally closed push buttons are presented in the program by the examine if closed instruction. Okay, so this one is XIC. This one is XIC. This one is also XIC. Yes, but the physical push button, one of them is normally open. The push button one is normally open one, and the other one is normally closed. But in the programming, we could represent both of these by XIC. So see what happens, yes? The normal state of the field input device, normally open or normally closed, doesn't matter to the controller. Does not matter to the controller. So this contact only examines if the contact is closed. If it's closed, then it's true. Otherwise, it's false. What matters is that contacts need to close to energize the output. So if we program this basically hardwired circuit like this, then the push button one, the first contact, this one, will be false, normally will be false, and the second one normally will be closed. Okay. So this one is normally closed. So this one is always true if we don't push this push button. Examine if open XIO instruction. The push button is represented in the user program by an examine if open instruction. So this is examine if open or negated contact. This is because the run must be true when the external push button is open and false when the push button is closed. Okay, so here, although the push button one is normally open, yes, but here, this XIO contact is true. The logical states 0 or 1 indicates whether an instruction is true or false and is the basis of controller operation. Okay, so when we have a logic 0, XIC is false, XIO is true because it's negated, and OTE is false, yes? 0, false. When we have 1, this one is true, this one is negated, false, and for this OTE, 1 means true. Okay, so here we have the same program here, and you see what's going on during scans. So the time aspect relates to the repeated scans of the program. Within the input table is updated with the most current stat bits. So here, at the initial time, XIC is false and XIO is true, so the OTE is false. Okay, so this one false, the second one is true, so this one is false. But as time goes, and the second scan, let's say the first one becomes true, and the second one stays true. So then OTE goes true. On the third scan, let's say the XIC stays as true but goes false, so then OTE goes false. And then on fourth scan, the XIC goes false, XIO stays false, and then OTE remains false, yes? And this is input bit status. You see the representative of the digital representative of false and true, 0 and 1s. And same here for the OT. Entering the ladder diagram. Okay, so here in a couple of slides, we see how we could enter a ladder diagram in Alan Bradley's RS Logic software. But later when it comes to the codices and TIE, you see how you could do the same on those programs. The concept will be very similar, yes. And the purpose of having these slides here is not to teach the software exactly, yes. We want just to get more familiar with ladder logic program. So Alan Bradley's RS Logic software packages are Windows programming packages used to develop ladder logic programs. Software in various versions can be used to program PLC 5, SLC 500, control logic, and micro logic family of processors. A personal computer is most often used and is adapted to the particular PLC model through the use of the relevant programmable controller software. RS Logic SLC 500 main window. So here you could see the main window, the ladder logic program, and instruction toolbar with bit instruction selected. Here, this is the instruction toolbar, and to place an instruction on a rung, click its icon on the toolbar and simply drag the instruction straight off the toolbar onto the rung of the ladder. Okay, so you could see all of that XIC, XIO, OTE, and other types that we haven't discussed yet of contacts and coils. Where you could find that software, you could find it in the CD attached to the main reference book, and you could freely install this software. The programming software needs to know what processor is being used in conjunction with the user program. The Select Processor Type screen contains a list of the different processors that the RS Logic software can program. Okay. The I/O configuration screen lets you double-click or drag and drop a module from an all-inclusive list to assign it to a slot in your configuration. This is the I/O configuration screen. Relay ladder logic is a graphical programming language designed to closely represent the appearance of a wired relay system. Yes, so we have repeated this sentence many times. And here you could see one example of these programs. The logic is apparent from the highlighting, which identifies the logic state of contacts in real time and which rung have logic continuity. So these contacts are false at this moment, and so the output, and these two contacts are true. The program shows the status, the logic status of these contacts by these two, let's say, green bars, highlighted bars. So the OTE here or the coil here will be true by going through the logical continuity on these paths. Modes of operation. A processor has basically two modes of operation, the program mode and some variation of the run mode. So here you can see program mode, run mode, and remote mode. Yeah, so we could switch between them. A 3-position key switch may be used to select different processor modes of operation. So you might not see the exact configuration on Siemens PLCs. Yep, so basically you could have, for example, run, memory, stop, and some other configuration that shows troubleshooting and communicates to the operator what's going on exactly in the program. But this one is just an example here based on the Allen Bradley's PLCs. The program mode is used to enter a new program, edit or update an existing program, upload files, and download files. So for some type of Allen Bradley PLCs, we need to put it in a program mode so we could upload or download files to or from PLC. The run mode is used to execute the user program. The test mode is used to operate or monitor the user program without energizing any outputs. Okay, and the remote position allows the PLC to be remotely changed between program and run mode by a personal computer connected to the PLC processor. So, new version of these Allen Bradley's Siemens PLCs might not have all of these modes. For example, on many of the Siemens PLCs, we don't have a test mode. To doing tests, we could use a simulation that will be topic of other sessions.